Imagine for a second that you are standing on a really busy shop floor.
Oh, the noise alone is something else, right?
Oh, yeah, it is deafening. But right in front of you is this massive, incredibly powerful machine, and it is spinning a sharp metal cutting tool at just absolute breakneck speeds.
We are talking thousands of revolutions per minute, literally tearing through solid steel like it is warm butter.
Exactly. Now, I want you to imagine that somewhere deep inside that spinning mass, there is an invisible, microscopic flaw.
Just something tiny.
Right, like a tiny scratch, or
Yeah.
maybe a slight loss of air pressure. And suddenly, that minor flaw just cascades.
Well, escalates so fast.
Yeah, the entire system begins to tear itself apart from the inside out. It ruins the expensive product you are making, destroys the internal mechanics of the machine, and, well, worst of all, potentially sends heavy, razor-sharp metal flying across the room directly at you.
It is a genuinely terrifying scenario. I mean, in the world of high-precision manufacturing, that catastrophic chain reaction is a very real risk, especially if operators are, just pushing buttons and not actually paying attention to the machine's physical state.
Which brings us to the mission of today's deep dive. Based on the notes, the articles, and the research you have shared with us, we are looking at the absolute core of a machining center, the spindle assembly.
The heart of the beast, really.
Yeah, the heart of the beast. We're going to figure out why this single component is essentially the beating heart of the entire operation. What happens when it starts to fail, how you can read a machine's body language to predict a disaster, and the incredibly high-stakes math involved in deciding whether to fix it or scrap it.
There is a lot of math involved, unfortunately.
There always is.
Okay.
Let's unpack this, because before we can understand how these spindles break down, we really need to understand the stakes.
The stakes are monumental. I mean, when you look at a machining center, the spindle isn't just another part on a schematic. It is the center of the universe for that machine.
Because it does all the heavy lifting.
Exactly. It has to hold the cutting tool with absolute rigidity. It delivers the raw rotational power, maintains flawless accuracy down to the micron, and then it has to seamlessly transfer the immense violent load of cutting metal back into the massive cast iron structure of the machine itself.
So it's basically the beating heart of a high-performance race car engine.
Hmm.
Like, everything relies on it.
Right. Without it, you just have a very expensive metal box.
But let me play devil's advocate for a second here. Put yourself in the shoes of a shop manager, right? You've got a massive deadline,
Right.
the client is breathing down your neck, and the machine is technically still running.
I know where this is going.
Right. Like, it is making a weird whistling noise, sure, but it is actively cutting metal. Why can't I just push through, finish the batch, and worry about the spindle on the weekend?
I see that temptation all the time on shop floors. And honestly, it is a trap. The most critical thing to understand is that a damaged spindle does not fail quietly for long.
It doesn't just hold out for you.
No, not at all. Trading a short-term output goal for a guaranteed catastrophic failure is just terrible economics. The damage happens in a very specific cascading sequence, and it accelerates the longer you ignore it.
So let's trace that cascade.
Mhm.
If I force the machine to keep running, it's not the safety hazard that hits me first, is it? Like, the product itself takes the first hit.
Yeah, the first casualty is always accuracy. Let's say a spindle bearing might be slightly worn or it loses its internal tension. Instantly, the whole cutting system becomes unstable.
And you can actually see that on the part.
Oh, absolutely. You will look at the workpiece and notice holes that were supposed to be perfectly round are suddenly egg-shaped. Or you will see these odd, repeating ripples on the machine surfaces.
Wow, so the dimensions just start drifting entirely outside of your acceptable tolerances.
Exactly. You are essentially manufacturing scrap metal at high speed.
Which is a huge waste of money. And since that spindle is physically bolted to the rest of the machine,
Yeah.
I assume the chaos doesn't just stay localized. Like, that instability becomes a pathogen.
That is a great way to put it. The loss of accuracy is directly tied to severe vibration, and that vibration travels. It tears through the machine's health, which is the second stage of the failure.
So it shakes itself to death.
Pretty much. The violent shaking damages the internal taper, the tool holder, the spindle box, the gears. Then those shock waves travel down into the guideways, the ball screws, and the delicate servo motors.
Jeez.
Yeah, you are effectively destroying the entire machine's anatomy just because you ignored the heart.
Then we hit the third stage,
Sure.
the one that clears the shop floor, right? Human safety.
The third risk is the most severe. At 10,000 revolutions per minute, if that internal clamping system fails because of the vibration and wear, the machine just lets go of the tool. Yeah, you get a tool fly out, a heavy piece of sharp carbide instantly turns into a lethal projectile. What's fascinating here is how the first loss, That slight drop in accuracy, those little ripples on the surface, is really just a warning shot before the final loss, which is human safety.
So continuing production is simply never worth the repair cost or the injury risk.
Never.
But if the consequences are literally explosive, how does a machine even get to that point? I mean, it's not like you walk in on a Tuesday and the spindle just randomly decides to explode. It is an accumulation of these invisible saboteurs.
Exactly. It's a slow build.
It reminds me of plaque in the arteries of our machine heart. Like it builds up silently over time.
That is a perfect analogy. Spindle damage almost always looks sudden to the untrained eye, but the foundation for that failure was laid weeks or months earlier. It usually starts with seemingly minor maintenance oversights.
Like what?
Well, lubrication failures are public enemy number one.
Because the spindle bearings are operating under immense stress, right? They require the exact right grease or oil in the exact right amount delivered flawlessly.
Flawlessly. If that oil is old or it gets contaminated with shop dust or microscopic metal particles, it is a disaster.
I imagine it just turns into sandpaper.
It really does. The contamination physically prevents the bearing from forming a stable oil film.
Right.
In a healthy bearing, the metal balls are essentially surfing on a microscopic continuous wave of oil.
Wow, surfing on oil.
Yeah, but without that film, you get raw metal-on-metal friction. Heat skyrockets. The bearing raceways and the rolling elements inside start to gouge each other.
So the spindle might still be spinning, but inside, it is actively grinding itself to dust.
Exactly. It is eating itself alive.
So that is the plaque in the arteries. Yeah. But looking through the sources, the taper hole seems just as critical. This is the literal physical connection point, right? The angled cone inside the spindle nose that grips the tool holder.
Yes. Think about a paper cup sitting snugly inside another paper cup.
Okay, yeah, they fit perfectly flush.
Right. That is how the taper and the tool holder interact. Now imagine dropping a single grain of sand into the bottom cup before stacking them.
Oh, I see. They no longer sit flush. They sit at a slight crooked angle.
Exactly. If that taper surface gets scratched, dented, or dirty, the tool holder cannot seat perfectly.
And if it doesn't seat perfectly, it is not spinning on a true center axis. You get eccentric rotation.
Which is what machinists call runout.
Runout. The tool is wobbling. So that damaged taper will systematically ruin every single tool holder you insert into it from then on.
It acts like a virus. And there is also the issue of bearing preload, which works hand in hand with that stability.
Okay, let's break down preload. Because as I understand it, preload is an engineered internal pressure applied to the bearings. It's as like squeezing the top and bottom of a heavy sandwich so the fillings don't slide around when you take a bite.
That is a very visual way to put it, but yeah, that is accurate.
It keeps everything tight and eliminates play under the violent forces of cutting metal.
Right. So when the preload decreases, the physical clearance between the steel balls and the raceway inside the bearing actually increases.
So things get loose.
Yeah, the spindle axis physically moves under the load of the cut. That introduces chatter.
That terrible vibration that ruins the finish we discussed earlier.
Exactly.
And we haven't even touched the automatic tool clamping system yet. Inside the spindle, there are these drawbar springs that provide the massive pulling force to hold the tool up inside the taper.
Right. They are incredibly strong.
And to lock it in place, those springs push steel balls into a groove on a piece called the pull stud. But over time, those springs fatigue. What happens if one of those tiny steel balls snaps under pressure?
Well, the grip becomes asymmetrical. The mechanism is no longer pulling the tool perfectly straight up into the spindle. It is pulling it slightly to one side.
Introduces microscopic wobble again.
Exactly.
Then you have the timing of the automatic tool changer. If the timing is off, I am picturing this mechanical arm trying to rip the tool out before the spindle's internal springs have actually let go of the pull stud.
It is brutal. The machine's arm and the spindle are essentially fighting a tug of war with a piece of solid metal. It rips at the pull stud and damages the clamping system.
That sounds incredibly violent.
It is. Add in deformed positioning keys at the spindle nose, and the tool holder will literally crash into the keys during a change. It makes a horrifyingly loud noise, deforms the metal, and basically guarantees your precision is gone.
It is wild to think about all these hidden variables. I mean, fatigue springs, bad grease, a tiny scratch on a taper cone, coolant leaking past a failed seal. Since these saboteurs creep in quietly, how on earth is an operator supposed to catch them before the spindle destroys itself?
Well, they do leave clues.
According to our notes, the machine actually talks to you, like its body language changes.
It does. A spindle will almost always give you clear warnings before a full catastrophic failure. Operators just have to know how to listen and what to feel.
Sound being the absolute fastest warning sign, right?
Oh, without a doubt.
Have you ever driven a car and known instantly, just by the sound of the engine, that something was wrong? You don't need a mechanic to tell you a sudden clanking noise is bad news. Here's where it gets really interesting, because the metrics of failure on a spindle are so specific.
They are very specific. A healthy spindle has a very distinct, steady, smooth tone. It might change pitch at different speeds, but the tone itself is clean.
So what are the bad sounds?
When you hear sharp metal friction, a rhythmic clicking, heavy knocking, a high-pitched whistling, or an uneven roaring sound, you hit the emergency stop.
Instantly.
Instantly. Those sounds mean bearing raceways are actively spalling, a bearing cage has shattered, or foreign objects have breached the seals.
That is terrifying.
And crucially, you will hear this long before a digital vibration meter triggers an alarm.
Wow, human ears beat the sensors.
Often, yes.
So you are listening, but you also need to be feeling. Heat is the second major red flag. And I am looking at these notes and I see a contradiction I want to push back on.
Okay, let's hear it.
The data says most machines need to stay below an absolute maximum of 60 to 80 degrees Celsius. But it also says if I see a temperature jump of 15 degrees in a 30-minute window, I need an immediate shutdown.
Right.
Wait, I am confused. If my machine normally runs at 40 degrees and it jumps 15 degrees to 55, I am still way below the 80-degree danger zone.
Oh.
Why am I hitting the emergency stop for a machine that is technically within normal limits?
It is a great catch, and honestly, it is a distinction that saves shops millions of dollars. The 80-degree mark is the structural melting point of the spindle's efficiency. But the 15-degree jump is a measure of friction going completely out of control.
Oh, I see.
Spindles are thermally stable environments. If a machine that usually runs at 40 degrees suddenly spikes to 55 in half an hour, it means a bearing has run dry, or contamination has just entered the raceway.
So the heat isn't the problem itself, it is a symptom.
Exactly. The heat is a symptom of a mechanical collision happening inside.
And heat causes thermal growth because the spindle is anchored at the back.
Right.
So as the metal housing and shaft get hot, they literally elongate. The metal expands forward, pushing the cutting tool deeper into the workpiece than the computer actually realizes.
That is exactly the physical mechanism at play. If we connect this to the bigger picture, it is not just about hitting a specific maximum temperature limit. The real key is noticing the rate of change from the machine's normal baseline behavior.
The machine is screaming that its internal geometry is mutating.
Yes.
And we can see this body language in the workpiece itself too, right? If your CNC program hasn't changed, your tools are sharp, your material is identical, but suddenly the hole diameters are unstable, that means runout has increased.
Yep. Or if you hear loud impacts during tool exchanges, that means the drawbar or the taper is failing right in front of you.
So once you hear the clicking, feel the heat spike, or see the ripples on the metal, you hit the emergency stop.
You have to.
Which puts us at a massive financial crossroads. Repair the spindle or completely replace it? Let's say my spindle just died and I want to save money. Why shouldn't I just send it to a repair shop every single time?
Because a bad repair decision buys you a repeat failure, which costs infinitely more in the long run.
So how do you decide?
The decision comes down to the depth of the damage, the potential for accuracy recovery, and the total cost. Repair makes perfect sense if the physical spindle body, meaning the heavy metal housing and shaft, is structurally sound.
So if the core skeleton is okay.
Right. And if the damage is strictly limited to where items like bearings, seals, drawbar springs, or cooling lines.
You mentioned the journal in your notes regarding structural damage. For those visualizing this, what part of the spindle is that exactly?
The journal is the perfectly smooth ground section of the rotating shaft that physically sits inside the bearing.
Okay, so it has to be flawless.
It does. If that smooth surface gets deeply scored or worn down, no new bearing in the world will sit flush on it.
I get it.
If the journal is damaged, or if the taper cone is so deeply gouged that it can't be ground back to factory specifications, repair is completely off the table.
Our sources also mention dynamic balancing as a mandatory part of a good repair. That is essentially like putting those tiny lead weights on your car's wheel rims so the steering wheel doesn't shake on the highway.
Right. That is exactly what it is.
Except engineered for a mass spinning at 15,000 RPMs, where even a fraction of a gram of imbalance turns into destructive force.
Precisely. A professional shop can replace the bearings, grind the components, adjust the preload, and perform that dynamic balancing to return the runout to factory standards.
So what is the rule of thumb on cost?
From a cost perspective, the general rule of thumb is that if the repair cost is under 30% of the price of a brand new spindle, you should repair it.
30% of.
Yeah. A repair might take 15 to 45 days, whereas procuring a brand new specialized spindle might take 3 to 6 months.
But downtime is incredibly expensive. I mean, we have to calculate the total repair cost, parts, labor, A&D, the financial loss of the machine sitting dead on the floor.
Yes, you have to factor all of that in. If that grand total exceeds 50% to 60% of the price of a new spindle, replacement is the much safer, smarter financial bet.
Just cut your losses and buy new.
Exactly. Furthermore, if you do repair a spindle and it fails again 2 months later, replace it immediately.
Why?
Because that pattern indicates deep internal metal fatigue or hidden structural bending that a repair shop couldn't see. In high-precision work, a spindle doesn't just need to spin. It needs to spin with unyielding, stable accuracy.
Wow. So if we know the math tells us to replace it once it hits that 60% cost threshold, how do we manipulate the variables on the shop floor to ensure we never even get close to that number?
Maintenance.
How do we keep the machine out of the repair shop entirely? So what does this all mean? To me, it feels exactly like brushing and flossing your teeth every day to avoid paying for a $5,000 root canal.
That is the perfect way to view it. Spindle life is entirely dependent on small, relentless daily habits.
Like what?
Well, the first one is cleaning. Every single day, operators must clean the spindle taper and the tool holder tapers with the proper cloth and cleaner.
So no skipping days.
No skipping. You can never allow chips, dust, oil sludge, or rust to sit on those precision contact surfaces. A dirty taper creates runout, and over time, that runout destroys the bearings.
Which goes back to the paper cup analogy.
Exactly. Never put a damaged tool holder into a good spindle. It acts like a virus, transferring the gouges directly to the machine's internal cone.
That brings us back to lubrication. I actually want to break down something fascinating from the research here.
Oh, about the grease.
Yeah. We established that too little oil destroys the film and causes metal-on-metal heat. But the notes say too much lubrication also causes heat.
Yes, it is a delicate balance.
When bearings are packed full of grease and spinning at tens of thousands of RPMs, the rolling elements have to physically ply through that excess grease, right? It's called churning.
Yeah, churning. That extreme mechanical churning action creates massive amounts of internal friction.
So it gets hot anyway.
It literally cooks the grease from the inside out, breaking down its chemical properties and destroying the bearing just as fast as having no grease at all. Precision is everything.
That churning grease generates heat, which means we have to talk about the cooling systems. Operators have to check coolant flow and the chiller status daily to fight that thermal expansion we talked about earlier.
They absolutely do.
And that cooling system has to work twice as hard if operators are pushing the cutting load beyond the machine's limits, right?
Definitely. Your speeds, feeds, and depths of cut have to match the spindle's actual power rating. Heavy cutting with a poorly balanced tool holder will obliterate the bearings.
Even if it doesn't look heavy.
Right. In high-speed machining, if a tool is unbalanced, the centrifugal force alone will destroy the spindle bearings, even if the actual cutting force on the metal is practically zero.
Which brings it all together with the final daily habit, inspections. Operators have to check seals to make sure no coolant or fine dust is migrating into the bearings. Check the clamping force of the drawbar.
Yep, all the boring stuff.
And the sources list measuring geometric accuracy, specifically perpendicularity and coaxiality.
Right.
To define those quickly for you, perpendicularity ensures the tool is exactly 90 degrees to the work table, and coaxiality ensures the tool is spinning on the exact same center line as the spindle itself. You compare how the machine performs today against its baseline from last month.
This raises an important question about shop floor culture. Are operators viewing maintenance as an annoying, one-time chore or an unbreakable daily routine?
It has to be a routine.
It does. That discipline is the only way to keep the machine accurate and keep those massive repair costs away. Knowledge is only valuable when it is actually applied on the floor.
It really is an incredible journey. I mean, we started by looking at this spindle as the beating heart of a massive machine. We uncovered those microscopic saboteurs, the churning grease, the single grain of sand of the taper cone, the fatigue springs.
All those silent killers.
Yeah. We learned how to listen to the clanking and feel the rate of heat change when the machine's body language shifts. We walked through the brutal math, of deciding whether to repair or replace the journal and bearings. Ultimately, we saw how disaster is prevented not by magic, but by the relentless discipline of daily rituals.
The overarching lesson here is that a damaged spindle will never fail quietly. The warning signs are always there. The operator just has to be willing to listen, understand the physics of what is failing, and act before it's too late.
Which leaves us with a thought for you to take away today. We spent all this time talking about machining centers, but think about your own life or your own business. What is your spindle?
Oh, that is a great question.
Right. What is that one central hidden component, maybe a key relationship, a core piece of software, or a fundamental daily habit that is quietly doing all the heavy lifting? What is the boring daily maintenance you might be ignoring right now, where just a little bit of attention today could prevent a total system collapse tomorrow? Think about it.